Welcome to section 9.2. In this video, we're going to talk about direction fields. So we're going to introduce direction fields and analyze them regarding the behavior of a DE solution curves. So with the differential equations, our task is to solve a DE, except sometimes we can't. Sometimes if we're looking at the DE, it's either impossible or just very difficult to solve, okay? If we cannot, then we have to resort to other techniques, right? And one of the really cool and visual techniques that we have here at our disposal is direction fields. And I want to illustrate what they are with an example. So what we're going to do is we're going to take some DE. So we're going to consider the DE y prime equals x times 2 minus y, okay? Now, there are ways of solving this that are not super complicated, and we can find the solutions in a different course. But for now, right, we're looking at this and we're like, okay, we're not gonna get an analytic solution right now. But what we can do is what we're gonna do is set up the coordinate plane, and at specific sample points, we're going to determine values of y prime. What y prime represents then is the rate of change at that given point. So hopefully that'll give us some information about the shape at those values. So here's what we're gonna do. So I'm gonna set up as best as I can a grid. And for each of these values, not all of them, but for a good amount of them, I'm going to try to find the y prime values, okay? So I'm specifically laying it out like this, not with hash marks on the axes themselves, so that I can see very clearly the direction field values, okay? So at each point on this grid, we're gonna set up little marks that represent the slope at that point. So for each y prime, we're gonna get a little line segment with the slope that we want, right? Okay, so notice for any x value equal to 0, right, regardless of whether it's 0, 0 or 0, 1, or all of those values are going to have 0 slope. So that right away is telling us the direction field values are 0 along that line, and so we get little straight across line segments, right? Now, for 1, 1, and let's just quickly do the calculation here on the side, right? So y prime of 1 comma 1 is 1 times 2 minus 1 equals 1. So at 1, 1, we have a slope of 1. Okay, what about y prime of 1, 0? So then we're plugging in 1, 2 minus 0, that's 2. So that's going to be more like this, right? And then y prime, negative 1, 0. Sorry, not negative 1, 0. 1, negative 1. That means we're plugging in 1 for x and negative 1 for y. So we're going to have 1 times 2 plus 1, which is 3. Okay, so it's getting sharper as we're going down here. So it's going to get steeper and steeper. And you notice that they will flatten out again because remember that as we're going up this straight line, y prime of 1 comma 2, we plug into 0, and that's going to give us another straight line. And that actually helps us to see that we have another set here over which we have just straight along flat little line segments that we want to represent here. Okay, not too bad. What about y prime at the point 1 comma 3? Well, that's going to be 1 times 2 minus 3, which is negative 1. So now it's negative. So there's like a reflection here that's going on, depending on where we're at in the... So relative to this line, y equals 2, the slopes were positive below it, but negative above it, okay? Let's repeat the same process on the other side of that line. So we're going to do the same calculations for x being equal to negative 1. So y prime of negative 1, 0. So that's going to be negative 1 times 2, which is negative 2. Something like that. What about y prime of negative 1 of 1? That's going to be negative 1 times 1, so negative 1. You'll notice that we're actually going to get a mirror image of the x equals 1 set. So if we plug in negative 1, right? So I'm looking at the one below the one I just drew. Or sorry, the one in the negative 1 spot. It's going to be negative 1 times, what is that? If you plug in negative 1, that's going to be 3, right? So it just keeps getting, the slope is getting steeper and steeper, okay? So mirror image. That suggests the pattern here. That means that we're going to get a mirror image across the the y-axis. And so if we get more points that represent what's happening here, so for instance, let's do y prime of 2 comma 1, right? So it's going to be 2 times 2 minus 1 is going to be 2. So that looks like this. What about y prime of 2 comma 0? So that's going to be 2 times 2 minus 0. That's 4. That's even steeper. So you'll notice that this does get steeper and steeper. Almost vertical. In fact, at some point, it's just going to be too hard to represent the slopes. Right? And it just keeps getting more and more dramatic, right? So for instance, plugging in 3 comma 0, so you give us 3 times 2, yeah. Practically vertical. And then we can mirror that on the other side, right? So it'll look like just a steeper version of what we have for the x equals negative 1 line. Okay, we filled out our direction field. Isn't that crazy? Okay, so this is the direction field. The direction field is the set of tiny slope segments at a grid of points that are sampled, right? So you'll notice some interesting patterns when we do this, because it'll suggest the shape of our solution curves. Namely, that we may have a solution curve that looks something like this. First of all, these are stationary curves, right? So first of all, we have the stationary curve y equals 2. We know that if we have the y equals 2, it's going to stay on that line. So think of it as like the little slope segments are suggesting where the solution should be. So it might look like this. Look like this. Now we know that because the slope on either side of the y-axis is going to be a mirror image of each other, we're going to get nice symmetry of our solutions. So maybe it'll look something like this, and it's going to correspond to some other curve that looks like this, right? Mirror images, right? And so while we don't have the explicit function that determines these curves, we do get an idea of the behavior. So a pattern usually emerges if we fill out enough sample points. And so doing this is, I think, maybe a little overkill for the usual kind of examples that we'll be using. But when you're setting up a direction field, you want to at least use enough points that you're getting a general idea of the shape of the solution curves. So I want to show you an example of what this is giving us. So another interesting concept here is that of autonomous differential equations. So when a dE doesn't depend on the independent variable, which can be x, it can be t, whichever it happens to be, right? It's called autonomous. Right. Autonomous. And so it has the form y prime equals f of y in the for first order. All of these that we're talking about are first order. So the result is the direction field that corresponds to this dE is going to have identical solution curves when we shift them horizontally, right? So as an example, we're going to sketch the direction field of y prime equals k 4 minus y 1 minus y. Okay, what this represents, by the way, is comes up in chemistry, where we're modeling the reaction of two reactants creating a single product. And so we may have an initial concentration equal to 4 moles per liter. And so this is the actual reaction, by the way. Now these arrows that I'm drawing here indicate in the initial concentration of the substances that we're talking about being 1 mole per liter. And then Y represents the concentration of C. Okay, so for simplicity's sake, we're going to let k equals 1. Okay, so this reduces down to y prime equals 4 minus y, 1 minus y. Okay, this doesn't depend on x, and this is the cool part. That because we're horizontally shifting, we just need to find a single vertical line and repeat that pattern across the x-axis. So for the sake of, seeing that, right, Let's go ahead and pick, so we're going to pick some points here. Say this is 4, 3, 2, 1, 0, -1, -2, -3, -4, okay? And, right, we're going to maybe do -2, -1, 0, 1, 2, 3, okay? We're not going to do all of them. Or actually, we are, but it won't be as painful as you think it will be. No, not what I wanted. Okay. So we'll move up and down the line for different values of y. We're going to use x equals 0 just for simplicity. So we're going to start there. So y prime of 0 is 4 times 1 equals 4. Y prime of 1, so that's one of the vanishing points, because when you plug in 1, that becomes 0. Y prime of 2 is going to be 4 minus 2, it's 2, times 1 minus 2 is -1, so -2. Y prime of 3 is going to be 4 minus 3 is 1, times 1 minus 3 is -2, -2. And y prime of 4 is 0, again. So it looks like this. 0, 0, not 0, 4. It's a pretty sharp, steep curve right there. At 1, it flattens out again. At 2, it's -2, -2. Okay, and if we repeat that pattern, right, across, remember that there are going to be identical line segments regardless of where along the x-axis you are, right? The only thing that matters is that if they're on the same y line, oops, then that part is the part that matters, right? So, all right, let's do the bottom part now. So now as we get further away from the equilibrium curves, so we get away from the y equals 1 and the y equals 4 lines, we're going to get something interesting, right? So it'll just keep getting steeper. So y prime of -1 is going to give us 4 minus -1 is 5, times 1 minus -1 is 2. Well, that's 10. Okay, so it's very steep at this point. Y prime of -2 is going to be 6 times 3, 18. Okay, at this point, we're just going to basically draw vertical lines. There's no sense in belaboring the point. But okay, so then now we can see that some solution curves, first of all, we have the stationary curves, or the equilibrium solutions, y equals 4 and y equals 1. This represents the fact that if we're equal to one or the other, then we're just not going to get any change. But on the other hand, if we're somewhere in between, oops, not what I wanted, somewhere in between, we drop down from 4 down to 1. So the 1 is going to be, we want to go down from 4 to 1. And similarly, oops, no, that's not the right. It's actually very steep. It looks more like this. So you can see a pattern emerges here where our solution curves want to get close to y equals 1. and our solution curves want to get away from y equals 4, right? Very interesting patterns here. Right, and so that's our autonomous direction field, because this pattern repeats regardless of where you are in relative to the x-axis, right? So no dependency whatsoever on x. All right, but that's enough on that. In the next video, we're going to talk about Euler's method.